Okay, Niccolò, can you share your screen?
Yes, 1 second. Okay, so
okay, so yes, so the second speaker of the day is Niccolò Cribiori from Max Planck Institute, and he's going to tell us about weak gravity versus scale separation. So Niccolò, please take off.
Okay, thank you, and thank you to the organizers for the invitation. It's my pleasure to be here and to have the chance of presenting my work. So in the following, I will talk about the interplay between two Swampland conjectures. One is the weak gravity conjecture, and the other are essentially various conjectures about scale separation. This is based on a recent work in collaboration with Gian Guido Dall'Agta, which appeared 1 or 2 months ago, more or less. So let me start by giving a bit of a broad introduction, so to give you some general picture and motivation for this kind of work. I think it's fair to say that there are at least 2 minimal requirements for doing phenomenology, and string phenomenology also. One is the absence of supersymmetry, so the fact that we don't observe supersymmetry. And this means that we should understand the way in which supersymmetry is broken. The other minimal requirement is the fact that we don't observe extra dimensions. And these 2 requirements might seem easy to implement in low-energy effective field theories, but actually one of the purposes of this talk is to show that this is not quite the case. So in fact, these are both often open problems when we want to understand them at a fundamental level. And in this talk, actually, I will not really discuss supersymmetry breaking. I will just concentrate on this second motivation here. So to be a bit more precise, I will consider the so-called problem of explaining this separation of scales. So there is no experimental evidence for extra dimensions, and yet string theory, or probably theories of quantum gravity, predict extra dimensions. We can put numbers just to give some order of magnitude. As for the observed dimensions, we can use as a proxy the Hubble radius, which is some 10 to the 27 meters. And of course, we don't know precisely the length of the extra dimensions, but as an upper bound, one can take the distances, the minimal distances probed by experiments. So for example, for LHCs, some 10 to the minus 18. So we have 2 length scales, which are very different. So there is a huge difference between these 2 numbers here. So this is an hierarchy problem. And this is what I will always refer to as the scale separation problem. And let me stress here at the beginning that understanding this problem and the origin of this problem is really crucial to define truly 4-dimensional effective field theories. So the moment we want to study 4-dimensional effective field theories, we have to be sure that indeed these theories are truly 4-dimensional and not secretly higher dimensional. Of course, let me also stress that an alternative would be so-called brainward scenarios, but I will not discuss this. I will only concentrate on string compactification. So I always have this picture in mind of having a 10 or 11-dimensional theory, which is then compactified down to lower dimensions, and typically I will take d equal 4. And yet, to be precise on what I'm going to discuss, for what concerns the precise definition of scale separation, I will take the following. So we'll consider some theories in d dimensions with gravity and scalars. The scalar fields are giving rise to a scalar potential. In this kind of theories, you can define a scale, a length scale, indeed what I called the Hubble length, which is roughly the square root of the scalar potential in Planck units. And then, given this scale, the requirement of scale separation is the requirement that the ratio of the Kaluza-Klein scale divided by the Hubble scale has to be parametrically small. So I will always consider situations in which I have parametric inequalities. And there is a subtle point here, which is indeed related to the Kaluza-Klein scale. So here I'm using the Kaluza-Klein scale as a proxy for the typical size of the internal compact dimensions. And this point is actually highly non-trivial. It is non-trivial, first of all, to determine precisely the Kaluza-Klein scale in general setups. This is typically a calculation which is model dependent, and typically is very hard to perform it where all of the possible effects are under control. Usually, proxy is taken to be like some power of the volume of the internal manifold, so 1/6 if the internal manifold is 6-dimensional. And this is the logic I will have in mind. So we take this as a definition of scale separation, but one has always to keep in mind that there are subtleties, especially in the definition of the Kaluza-Klein scale. Now, I will also take an even more modest attitude because I will concentrate only on a maximally symmetric vacua. Maximally symmetric vacua can be de Sitter, Minkowski, or ante de Sitter. However, it's fair to say that it's not clear whether we can have really controlled example of de Sitter vacua in quantum gravity and string theory. And moreover, when you address de Sitter, you also have to somehow to solve the other problem I was mentioning at the beginning, so the understanding the breaking of supersymmetry. So we'll not consider de Sitter. Minkowski vacua, if you use this definition, then Minkowski vacua will be automatically scale separated. So this is not really an interesting case to be studied. And then I'm just left with ante de Sitter. So ante de Sitter vacua are indeed an interesting playground to study the problem of scale separation. And still, it's something non-trivial can go on there. Of course, these are not realistic because we observe a positive energy density. But aiming at some more phenomenological purposes, one can recall that ante de Sitter vacua are still part of important constructions like KKLT or LVS, which aim at describing de Sitter instead of ante de Sitter in string theory. So this analysis can be also relevant for this kind of constructions in principle. Moreover, I will concentrate on ante de Sitter vacua with supersymmetry. And again, this in order to have some more control on my setups and in order to be able to perform computations. And then, of course, the problem can be addressed both from lower dimension and also from 10 dimensions. But again, due to reasons of time, I will only address the problem from lower dimensions. So we'll take what is called a bottom-up approach. In this approach, you would like to construct an effective field theory which is consistent with quantum gravity, but many things can fail, as it is well known. And all of the point, indeed, of the Swampland programming is to try to capture which are the consistency criteria which are needed in effective field theories in order to be consistent with quantum gravity. Among these criteria, I recall actually now the weak gravity conjecture, which is among the most robust and well-tested conjectures in the Swampland program. And actually, I will use the so-called magnetic version of the weak gravity conjecture. The magnetic version of the weak gravity conjecture is saying that the cutoff, the UV cutoff of a given effective field theory is actually bounded by the gauge coupling of the effective field theory itself. So in the moment I have a gauge coupling, an abelian gauge coupling in my theory, then I have a bound on the UV cutoff. For the scale separation in the Swampland program, there are also other conjectures which are relevant. There is a considerable amount of works. Here I'm summarizing some of the authors and some of the names, but the list is much longer, probably. And essentially, the message in one single line of all of these works is that there should be some relation of the kind I'm showing you here. So there should be some relation between the Hubble scale and the Kaluza-Klein scale with some parameter alpha, which might be model dependent. But still, the existence, if proven, the existence of this relation will tell us that it's not really possible to decouple these two scales. And so it's not really possible to have scale separation. Well, of course, all of these conjectures are a bit less tested than the weak gravity conjecture. And then in the rest of the talk, I will not assume any relation of this kind. Rather, I will assume the weak gravity conjecture to hold, and then I will use the weak gravity conjecture to derive a relation of this kind. So I will thus make a connection between the weak gravity conjecture and scale separation, and I will derive precisely this kind of relation without assuming any other Swampland conjecture. And this is essentially the logic behind this work in collaboration with Gianguido Dell'Agata. Now, the strategy, as I was saying, would be to consider four-dimensional supergravity with supersymmetric anti-de Sitter vacua. And then the idea would be to exclude the presence of scale separation by using the weak gravity conjecture. And in order to do so, I will have to restrict my attention to what is called extended supersymmetry. So n=1 minimal supersymmetry in 4 dimension can still possibly evade the argument that I'm going to present. But in the paper, we have a complete argument for n=2 and also n=8, and also we discussed the cases in the between. And the argument essentially amounts to showing that the cosmological constant in this kind of vacua can be expressed always as a product of the charge, of the U1 charge, of the U1 gauge coupling, of the weak gravity conjecture, and the Planck mass. And there is no other parameter entering this relation. So there is no way in which I can tune this number, essentially. And then once I show this relation, I can enforce the weak gravity conjecture, and I can replace the gauge coupling with the UV cutoff with an inequality. And then I'm in a situation in which the Hubble scale is of the order, or probably even bigger than the UV cutoff. This might be already worrisome, but then let's say one can keep going. And still, if we use supergravity as an effective field theory, it's natural to say that the UV cutoff is actually the Kaluza-Knight scale, is the first natural cutoff one can think of when using supergravity. And then plugging this relation inside here, we see that scale separation in the way I defined it before is automatically excluded. There is one hidden assumption here, which is related to the charge. So the only parameter entering this kind of relation is the charge. And then I have to assume that there is some sort of charge quantization undergoing this setup. This is natural in quantum gravity, where all charges are quantized. And actually, the precise details of the charge quantization are not important for the argument. What is important is that I cannot tune this number to be very, very small arbitrarily. And as I was saying, and as I will discuss also at the end, anti-de Sitter vacua with no supersymmetry or minimal supersymmetry in 4 dimension might still evade the argument. So before presenting the argument, I need to review in one slide few ingredients of supergravity, which are then appearing in the derivation later. So the theory is fixed by a function which is called prepotential. F is a function of the scalars x, or equivalently, you can specify what are called symplectic sections, which are essentially given by the Kähler potential k, and then you have again the scalars x, and these f lambda, you can think of them somehow as the symplectic duals of the scalar. So in n=2 supergravity, there is some notion of symplectic transformations. The theory behaves well under the symplectic group, and then you can define these vectors. Alternatively, you can think of these f's as the derivatives of the prepotential, but this is a bit more subtle. The other ingredient I need are the gauging. So in n=2 supergravity, and n bigger than 2 also, so in extended supergravity in 4 dimensions, it's a fact that in order to have a scalar potential, you need to gauge some of the isometry of the scalar manifold. So if I want to have anti-de Sitter vacua, then I must have some gauge group in the theory. This is not true, for example, in n=1 because we have a superpotential. Now, which kind of gauging, how the gauging is constructed? There are 2 ingredients which are independent. So since we have vector multiplets and hypermultiplets, I can gauge isometries on the vector multiplets or of the hypermultiplets. So I have 2 different moment maps, P0 here and Px here. And then I have 2 different killing vectors, which are the derivatives of the moment maps. Also, I need to recall, this will be important, how the scalars in the theory couple to the kinetic terms of the vectors. So there is a matrix, the imaginary part of n, this is usually called also the period matrix, which is encoding the coupling of the scalar fields in the vector multiplets to the kinetic terms of the vector. And then it is known that the full form, the full expression of the scalar potential in n=2 supergravity is this line I'm showing you here. This is of the order of the gauge coupling square, because indeed, if I turn off the gauging, this scalar potential is identically vanishing. And it is a sum of 3 different contributions. We have the gaugings on the vector multiplets, the gaugings on the hypermultiplets, and then there is a third contribution, which is actually the one which is important for us. So the first two and second term are not important. I will concentrate really on the last one here, the one in red. And this term with a minus sign in front is essentially the gravitino mass. So this is just, if you want a more complicated way to write the gravitino mass in n equal to 2. So this is the form, the specific form the gravitino mass is taking in n equal to 2 supergravity. So why I'm concentrating on the last term? Because again, it's a fact that in n equal to 2 supergravity, and in general in supergravity, the vacuum energy of a supersymmetric anti-de Sitter vacuum is given precisely by the gravitino mass. So the moment I'm concentrating on just supersymmetric anti-de Sitter vacua, I have a drastic simplification of my scalar potential, and I have just this term here. And up to here, the analysis can be pretty much generic for any numbers of supersymmetries, but then I will use now the advantages of having n equal to 2 with respect to n equal to 1, for example. So in n equal to 2 supergravity, we have some nice relations which are based on the underlying special geometry. And for example, you can write the gravitino mass here in terms of the gauge coupling. So you can show that there are identities, really algebraic identities on the scalar manifolds of this type. So the first step is to pass from a cosmological constant given by a mass, or gravitino mass, to a cosmological constant given by the gauge couplings here. Then up to here, this is completely generic and it's valid for any gauge group, even on abelian. If, however, I want to use the weak gravity conjecture, I have to identify an abelian gauge group. So first of all, of course, I have to require that there is an unbroken abelian gauge group. This will be an assumption. But then I have to identify this. Again, this can be done in general. So I can identify some generic linear combination of the vector fields. A, lambda are the vector fields and theta are coefficients. I will call this vector the weak gravity conjecture vector, and this will be the direction along which the weak gravity conjecture U1 factor is lying. If then I canonically normalize the kinetic term of this vector, I can read off the gauge coupling entering the weak gravity conjecture, which has this form in terms of n equal to 2 quantities. And once I'm here, I'm almost done, because then I just have to split the gauge couplings into directions orthogonal and parallel with respect to the weak gravity conjecture. So using the properties of these quantities, for example, the fact that this matrix is negative definite, one can write an inequality of this type, keeping only the part along the weak gravity conjecture direction. And then once one is here, the only remaining step is to canonically normalize everything, so to recognize the gauge coupling and the charge, and then with the correct redefinitions, one arrives here. So the full vacuum energy in supersymmetric anti-de Sitter vacua is given by this combination of the gauge coupling and the charge. And then the argument is done essentially, because one can take the absolute value, flips the sign of the inequality. So we have that the vacuum energy is actually bigger than the gauge coupling and the charge. And then by enforcing the weak gravity conjecture, one shows that the vacuum energy, so the Hubble scale, is of the same order or perhaps even a bit bigger than the UV cutoff of the theory. And then again, as I was saying, if the UV cutoff, as it is natural to assume, is the Kaluza-Klein scale, then these vacua are not scale separate. So this is essentially the argument in 2 slides, which one can use to show that in n equal to 2 supergravity with generic gaugings in which there is an abelian gauge group unbroken in the vacuum, then supersymmetric anti-de Sitter vacua are not scale separate. Let me give you an example before discussing generalizations. So it is known that M theory on Sasaki-Einstein manifold gives rise to 4-dimensional equal to 2 supergravity with various abelian gaugings. Here are some of the works which can be read for examples. As I was saying, you need to specify a prepotential. In this case, this is the prepotential. You have 2 scalars x0 and x1. This is the function of the scalars which is given the prepotential. Then there is a quaternionic manifold with this metric. The details are not really important. What is important is that there is an abelian gauge group in the vacuum, which is good for the argument to apply. And then you just have to identify the quantities I was giving you before. So you need to identify the moment maps and then the gauge coupling and the charge. It turns out that the moment map is something like this simple vector here. And then it's just a matter of doing the computation. You can show that the vacuum energy, which is -12 in some unit, can be understood as being actually -6 times the gauge coupling and the charge, where these are really the gauge coupling and the charge with respect to IU1 factor. And so these kind of models are precisely of this generic form here. And then this shows that these models are not really four-dimensional effective field theories. Of course, this can be still consistent truncation, but they cannot really be used as truly four-dimensional effective field theories. So there are various ways in which we can generalize this. In the paper, we also present the same argument for N=8 supergravity, which is the maximal theory in four dimension. So the same argument works also in the maximal theory. So we proved it for N=2 and for N=8 completely. And then we give evidence that it should work for all this amount of supersymmetries in the between. So from N=2 to N=8. Of course, a complete analysis will be quite long and probably even a bit model dependent. But still, we believe that there should be no big obstruction in proving this. Another generalization, which we believe to be straightforward, is to extend this to dimensions bigger than 4. And actually, there is a nice mechanism going on, because if you extend this, let's say, to 5 dimensions, then at that time, you can already exclude N=1, for example. So minimal supersymmetry in 5 dimensions would be excluded by this argument. And then let's stay again in D=4 for phenomenological reasons. As I was saying, there is still the chance that N=0, so no supersymmetry or minimal supersymmetry, can evade the argument. And this seems to be compatible with the fact that there are indeed known classes of scale separated under the Sitter vacua in string theory. And these vacua in 4 dimensions indeed have either N=1 or N=0. So the two results are still compatible. And before concluding, I would like also to, just in one slide, to show that a very similar argument can actually be used to exclude the Sitter vacua. So something which seems to be completely different, but still in supergravity, you can use some similar reasonings. So this is just one slide. The way to proceed is the following. The first observation is that in the Sitter, there is some sort of natural IR cutoff, which is again the Hubble scale. So the Hubble scale is entering again with a different motivation. Then there is one more assumption I have to make with respect to the anti-de Sitter case. I need to assume that the gravitational mass is vanishing on the vacuum. So we'll just concentrate on a subclass of models in which the gravitational mass in the scalar potential is exactly 0. If you do this, under this assumption, then the scalar potential is in a correct form to exactly repeat the same steps as before. So identify the weak gravity conjecture U1 vector, then you split into contribution orthogonal and parallel with respect to it, and then you neglect some contribution, you write inequalities, and then you arrive at a relation of this type, that the cosmological constant is given by the gauge coupling and the charge. So the cosmological constant is actually of the same order as the UV cutoff. And then, since the cosmological constant is indeed the Hubble scale, and then it's the IR cutoff, you are in a situation in which the UV cutoff, sorry, is actually of the same order as the IR cutoff. So if you want to use these kind of theories as effective field theories, then these are not really good effective field theories, because it means that they are not really protected against corrections, because essentially there is no room in which these theories can live in. Typically, you would like to have some parametric separation between these two scales. And again, similarly for anti-de Sitter, so there seems to be some interplay, some analogy between scale separation and de Sitter by using the weak gravity conjecture. The only chances to evade this argument is to have N=0 or 1 supersymmetry at the Lagrangian level. So to conclude, scale separation, it's a minimal requirement for phenomenology in theory with extra dimensions. And I hope that I showed you that, contrary to what one might naively expect, obtaining scale separation is already hard at the level of 4-dimensional effective field theory. So when doing bottom-up, purely bottom-up approach. In the paper, we gave evidence indeed that scale separation is not possible for supersymmetric anti-de Sitter vacua from n equal to 2 up to n equal to 8. And still, as I was saying, it seems that the most promising chances to get scale separated anti-de Sitter vacua in 4 dimensions are theories with either no supersymmetry or minimal supersymmetry. So these, I think, are the most interesting scenarios to be studied further in order to better understand the fate of scale separation. Thank you for your attention.
Thanks, Niccolò, for the very nice talk. Are there any questions for Niccolò? One quick question. So if there are no questions, I have one. Right. So there's been an argument trying to argue along the lines that with higher supersymmetry is difficult to get scale separation, precisely because you expect a tower of R-symmetry charged states. So just from the superconformal algebra, you find that the BPS bound predicts a tower of states, and if those charge sites are populated, then that tower of states are typically geometrized, and in any case they are against scale separation. So the cutoff that you find is basically magnetic weak gravity for the R symmetry, right? So it's basically the same as that tower stays, correct? Or
yes, yes, probably that would be some sort of electric version, probably, if I understand correctly. What
yes, right. So the point is that the magnetic weak gravity, the cutoff of magnetic weak gravity can, in principle, not be exactly what one gets from just the gauge coupling. If for instance, there's like a discrete version of the electric things, so there can be factors, there can be discrete factors that can lower it up. So in the end, I think it's the same physics as the power of states. Yeah.
Yes, I think so. Yes.
Okay, thanks. Any other questions for Niccolò? Well, if not, thanks a lot again to both Niccolò and Alvaro for the very nice talks. And I just want to encourage all of you to apply to give talks at our seminar series. Please do so. I think it's a good platform. Okay, so see you next week.